We'll start the webinar in just a few moments.
I think next time, Tina, we need some countdown music too.
I know, we'll have to add that in. It's some sort of theme song.
No. Elevator music. That's where it's at.
Yeah. All right, people are still coming in. All right, and we'll get started. So hi, everyone. Thanks for taking the time to join us today. We'll be starting the webinar in just a few moments. My name is Tina Fabiano, and I'm on the enDAQ Marketing and Engagement team. In a minute, Steve Hanley, our Vice President of Product, will be presenting today's webinar and Q&A session on simplifying vibration and shock analysis with the enDAQ Python library. We're really proud and excited to be sharing our new open source Python library with you today and demonstrating how this package helps you directly load and parse data from IDE files, generate power spectral densities and shock response spectra, double integrate into velocity and displacement and resample data, and how this library and its functionality really helps you to conveniently analyze shock, vibration, and other sensor data and adapt your analysis to meet the needs of your application. In addition to Steve, we also have Becker Alcati, David Stokes, Connor Flanagan, and Sam Ragusa with us as panelists. They're all in the enDAQ software team who developed this library, so we're excited to have them with us to answer your questions as they are incredibly knowledgeable on this topic. This is a 45-minute session. As you're watching the webinar, don't hesitate to use the question and answer button labeled as Q&A right at the bottom of the screen. The software team is monitoring the questions that come in and will be able to answer some of them in real time. Then Steve and the team will answer any other questions at the end of the webinar. We'll also have some poll questions for you to answer, and at the very end, we'll launch a post-webinar survey. We'd love to have your feedback so we can make sure we're providing you with relevant resources around this topic, and so we can continue to improve our content. We're really excited to be running this webinar today and answering your questions and helping you simplify your vibration and shock analysis with the enDAQ Python library. So with all that, I'm happy to introduce Steve Hanley, who'll be taking it from here.
Hello, everyone. Thank you, Tina. As Tina said, I'm presenting it, but this has been a big effort by the software team who I'm joined with on this webinar. So we'll be able to answer your questions as they come at the end and as well as beyond. We'll be supporting this and adding functionality as we go. This is in a Google Colab link that we're sending out. So I encourage you to kind of play along as we go and try out some analysis in real time. Skip ahead if I'm boring you and check out some other stuff we'll be covering later. But what are we covering today? So we're going to start really by focusing on the enDAQ library and all the capability. I'm just going to launch a quick poll because before we're presenting this webinar, we've done 3 other related ones to introduce Python to maybe many of you mechanical engineers out there that were unfamiliar with it. So that was one webinar, and then another one, we did some data analysis with NumPy and Python or pandas. And then we did some plotting with Plotly in our 3rd webinar, and that was all really laying the groundwork for this one today. So I'm curious if you've attended some of those previous ones, if you have some familiarity with Python. If you do, great. If you don't, I can try to kind of remind people throughout the webinar places to check out after to familiarize with certain things. So I'm going to actually, as a poll is going on, what am I going to cover today? I'm going to go through, why we developed this, and then the documentation of the code, and then really get into all the examples. So I have a few different stories. One is you have a large data set, you want to do some frequency analysis of it. Another story is you have 3 different recording files and you want to compare them to each other. Another story on shock analysis. Another one where you have a moving frequency and you want to understand what happened there. And then the last story is with some sound data. Sound is very much part of shock and vibration analysis. So hopefully that's helpful too. So let me end the poll and I'll share the results. So we have a lot of you that have attended some of the previous webinars, which is great, but almost half of you, or more than half of you, this is the first one. So that's also totally cool. There's a good mix of people that have our devices and don't have our devices. So I'll highlight that our library is useful in both cases for sure. We made sure that the enDAQ library isn't just for our customers, and I can explain that as we go. And then a lot of you have little to no experience with Python, but that's really fine and what we kind of aimed this library to cater to. So let's get into it. Why do we develop this open source library? Well, when you're analyzing data, you typically are going to need to do a few things. One is you're going to need to customize the analysis to meet your specific need. You also want to share the results. So it's helpful when your plots can be interactive with other colleagues you're sharing with. But then most importantly, you want to share the methodology with how you got to those results. If we're sharing this with a nice plot with an engineer, colleague, or customer, they're going to want to dive into the layers to see how you got there. You'll also want to reproduce the analysis for future data sets and other data sets. And that's really where a Python script can help in all these areas, is reproduce testing, generate these shareable plots, but also well-documented notebooks so you can explain exactly what you're doing and why. And then the enDAQ open source libraries is kind of adding to the Python world to make it even more convenient and adaptable to analyze shock and vibration and other sensor data. All of our documentation is hosted at docs.endaq.com, which is here. So definitely check that out. It's really well documented. I linked to it throughout the webinar. I'll just quickly touch on the fact that the enDAQ library has a few modules within it. The first is enDAQ.ide, and this is where there's some functions to pull data out of our IDE files that are generated by enDAQ recorders. Then there's enDAQ.calc, which is doing all the analysis, filtering, power spectral densities, integration, things like that. The interface into enDAQ.calc is now disconnected from our devices. So you don't need to have data from our devices to use these functions. You just send it in data frames of data. And then there's enDAQ.plot, which similarly is the interface. There's data frames to generate the plots, or dictionary of data frames. So again, it's a little decoupled from our devices, and I'll go through a lot of functionality there. We also have enDAQ.cloud, which we'll cover in a future webinar, and that's interfacing with our cloud API. We're not going to really talk about that much at all today. Okay, you want to start using our library. How do you install it? Well, it's available on PyPI. So you pip install, which is pip install enDAQ. If you're running locally, you just need to do that one time. In Google Colab, with this kind of server hosted notebook and Python environment, you need to install it every time. You also need to reset the runtime. That's why I did this exit function. But after that, then you can load in the library, which is import enDAQ. And then there's all these other libraries which we've covered in previous webinars. Plotly for generating our interactive plots, NumPy and Pandas for kind of structuring our data and analyzing it, and SciPy that has some higher duty analysis capability. And really our enDAQ.calc uses a lot of SciPy functions, but simplifies the interface. Okay, let's get into it. So if you're one of our customers, you'll need one of these. The first function here is enDAQ.id.getDoc. So this is getting the object of the data that's within your .ide file. And so I'm right now pulling in a file that's hosted online, but you can pull in, load in data that's locally hosted. I just want to call out for people that are new to Python, you need to do the double backslashes for local data sets, which can be a little bit cumbersome when you first get started. But if you're running a Python script in one folder that the data also lives in, you don't necessarily need to worry about the file, the backslashes. But this getDoc function is really helpful. David did a really good job on it to allow you to either be pulling in locally hosted data somewhere online, as well as even Google Drive, which has some kind of funniness to it. So this is a really simple and interface to get the object of your data out. I know not all of you are customers, so I'll come through here, but I do want to call out that once you have the object of the data, there's some elements or methods associated with that is nice. So you can see what was the part number of the device that recorded this data, the serial number, and what's helpful to remember is that lives inside the file. It's always with the data. which is nice to know the serial number. And there's other parameters like the data was recorded, the data was manufactured, firmware revision, things like that. All right, so you got the data in as this object. What is inside of it? You want to look at the data. The first function we have is this get channel table, which presents this table of all the subchannels that are in the file. So you see the channel numbers, the names of the subchannel, the units, how many samples are in it, what the sampling rate. And so this can help you get an idea of where you want to further analyze. For folks that want to filter this table, you can. You just have to use table.data. But presumably, you're going to want to get the actual raw data out to do some analysis and plotting. And so here, we're pulling in for every channel. This is, if you're new to Python, this might look a little funny, but it reads well if you kind of look at it a couple of times. So for channel in the doc.channels, we're going to make this dictionary where the key is going to be the name of our channel. And then the value is this data frame of the data. And so this is another function in enDAQ.IDE, which is 2 pandas. So it pulls out the data of a channel or a subchannel into a data frame. And you can specify whether that time axis or the time index is either date time objects. This is real calendar time. Or if you said date time or time mode equals seconds, it would just be number of seconds into the file. But from this point on, if you're not a user of our devices, you just have a dictionary of data frames. So it doesn't have to be from our device anymore. Once you have this dictionary of data frames, we have this function that I'm really excited with Sam. He did a great job on this rolling envelope dashboard. So there's a lot of data in here. There's 13 million samples in one of the data frames. One of the other data frames has another couple million samples. It's a lot of data to plot. And if we were trying to plot all of that in Plotly, it might crash Plotly. It would take a long time to present. It would be very sluggish in our browser because it's trying to render all the data. But this function does a nice job to break the file into a defined number of segments. Here I'm saying I just want 100 windows. And then for every window, it basically plots this bar graph that goes from the minimum to the max. And so when you're zoomed out, if I made it more granular and did 1,000 windows, the zoomed out view is going to look pretty much identical to if you actually loaded all the data and plotted all of it. There's some other really nice ways to customize this view. You can define how wide every subplot is, whether you want to do rows, columns, 3 rows, or 4, and all that's available to you to define. So here you get this dashboard of all the data that's in this dictionary data frames. Again, so for this use case, it's from a 140 megabyte IDE file, but it could be from any data, and I'll show that in a second. Another function we made that I really like is the theme. I really like to make my plots look nice and consistent, and so we made this function to define 4 themes: enDAQ, enDAQ Lite, and then there's 2 other versions that are very similar. They just have a different font. So when you're in the cloud, it uses Open Sans. So if we call this theme, this function is going to create these 4 themes and make one of them the default. So if I update my figure above, I can use the enDAQ theme, and I have some nice styled plots with nice colors and background colors. Remember, these are Plotly figures, so you can save it to an HTML file, and then you could share it with a colleague, and all the interactivity is still retained. So it becomes really nice for colleagues and customers to share and experience the data. As I mentioned, this function has a lot of user-defined parameters to it. So here I'm showing you what happens if I say, I don't want to plot this as bars. I just want to plot the moving max and the moving min as 2 separate lines. And I want to just do 1 row, so it's not this kind of sub grid. And here you go. As I mentioned, it doesn't have to be from our data. Here I'm making a dictionary of data frames just from a bunch of CSV files. So I have a CSV of acceleration data from a crash test, CSV of motorcycle, so, like the 8 or 9 files here. And then I create that dashboard again by passing in this dictionary. And then I have this nice way to compare many different files in this one dashboard. Okay. A related function is if you want to plot some metrics. Let's say right in that last function, we were plotting the max to the min. But what if we just want to see the rolling standard deviation of the rolling max, absolute value, or mean? So there's this other function here to do that, and then we see how the max or mean or standard deviation changes. All right, let's go back to our big data set. Again, it's in the dictionary data frames. So I can see the keys. These are all my channel names. And if I want to pull out just one data set, in this example, I'm primarily interested in that primary accelerometer. So I just say data and the 100G PE accelerometer. Now I have my data frame. If you already know kind of going into it, which channel of interest you have, you can use that 2 panas just to get that acceleration data. But again, it doesn't have to be from our devices. Any data set will do. So you have this data frame now of acceleration data. First thing I'm going to do is apply a high pass filter. I want to get rid of the DC offset, any weird bias issues. If you notice in those previous plots, there's some weird things going on with the DC offset. So I want to get rid of that. In general, you're probably better off doing a high pass filter on every data set pretty much. So here we have a function in enDAQ.calc to do this filter. I pass in the acceleration data and I say a low filter cutoff of 2 Hertz. And then I get a data frame back of the filtered data. And here I'm going to plot this entire data set in a similar function to the dashboard, but instead give me all my columns of data in one plot. And so this is 13 million points per channel. So that's a lot of data to plot. And when you're zoomed out like this is going to look identical again to if you plotted the entire thing. Yet you have the interactivity. You can isolate one of the axes. There's a function or a parameter here for the opacity. I don't know how to pronounce that. Where you could make it not opaque at all, so it's just completely shaded through. But then that matters what the order of plotting is. But in any case, this is really nice. I think this is a really powerful feature and function for anyone that has a lot of data that they want to plot in the time domain. You still have the interactivity. You can zoom around and understand where some areas of interest are, and then focus that with your later analysis. You got all the data, and you want to do a PSD. So we have a function in enDAQ.calc to do that, where we just pass in our acceleration data, and we say the bin width of 1 Hertz, or 0.5 Hertz, or 2 Hertz, or 3 Hertz, whatever we want as a coarseness to our PSD, we can define here. When we're looking at triax accelerometer data, you often want to look at the resultant. The resultant's the square root of the sum of squares. But when you have a PSD, you already have squared terms, so you just have to sum the squared terms and you get the resultant. So we can just add that to our data frame. And now we can plot it really easily. I have a lot of plots in this notebook, so probably might have issues sometimes. So here's my PSD of the entire data set. 13 million points reduced down to this 4,000 point PSD. It's interactive. I can zoom around. I can save this as an HTML file. I can share with colleagues, etc. Now, this is still a lot going on in this power spectral density. A lot of times people want to reduce their PSD into a number of points that they could put into a shaker table to reproduce. And you're not going to necessarily enter in all 4,000 points. So you could convert your linear space power spectral density to a log space one, which we're doing here. So once you have your PSD, you send it into enDAQ.calc.psd.toOctave. And you say, okay, I want to start at 4 Hertz. I want to have 3 bins per octave. And then you get this reduced PSD back. And here I'm adding to that figure above this octave space power spectral density. So here's the x-axis linear space data, and here's the log space data now. You see it's a lot cleaner. I could even go a little bit more granular, which I'll do in another example, to really reduce the number of breakpoints. And that toOctave function does it still maintains that same cumulative energy, the cumulative RMS of either the octave space or linear space PSD will be the same. One of the reasons I like this data set is because it was big, but it also has a lot of different frequency components to it. And we have another function in our plotting library, enDAQ.plot.octave spectrogram, that is generating a spectrogram, but it's doing something pretty clever here to allow you to have log-spaced frequency bins. And that's helpful for 2 reasons. One, when we look at frequency content in the vibration data, we want to look at it in a log scale typically. And then 2, when we're looking at the log scale, like it reduces the amount of data we have to present. So I can generate this spectrogram and I have the interactivity, and it's not going to be really sluggish to show me all that content. And by the way, this takes 3 or 4 seconds to generate and present to you. And you see here that this data set, it's on some motor, and there's different RPM levels throughout the test. And so if you're one of our customers, you have a big file, our devices record a lot of data, you may want to pull out a subsection of that file for, in this time of 9:17, 15 seconds into 9:17:25, there's 10 seconds of data there that is when my engine's at this operating state, and I care really much, I care a lot about that, and I want to share that with someone else. I don't want to send them a 140 megabyte file, but I can send them, a 1 megabyte file of just the area of interest. And so we have a function. David did a really good job on this. It's really nice. Check out the docs. It's really well defined how you can use this to kind of extract just a subsection of a file. But once we're in, Python, we can kind of slice and dice here as well. So if I want to do a PSD of just that time range, I can index that with my pandas data frame here. And you see here, there's that low frequency component around 31 hertz, which we see here in the spectrogram. But if you come up all the way here to the PSD of the entire file, you don't really see that frequency, and that's because it's really kind of muted out by everything else. So I'd always cringe a little bit when I see our customers have a large data set and just calculate one PSD on it. That can really mask some other things that are going on. So I encourage you to do a spectrogram, just make sure things are consistent. And we'll add some other functions too to show you how a PSD moves through time, things like that. Okay. One thing I want to call out here is, I can't reset it, but if you just ran this on your own machine, you'll see that this, let me see if I can refresh this. There's a light sensor in our device, and every time the motor was on, the light sensor was updating that plot, or it has different lux levels to it. And I thought that was pretty clever. Let's see if it loads now. So I just want to call out that customer that was using that, whether it was purposeful or not. It was pretty cool. Let's see. Anyways, okay, so that's story one. Story two, let's see how I'm doing on time, is we put 3 devices on a shaker table, one in the middle to really measure what the shaker was doing, and the other 2 on different length aluminum beams. So they're going to have different natural frequencies. And so let's say I want to compare these 3 data sets. So I only care about my my accelerometer data, so I can load just that channel from every file, which I'm doing here, and I'm putting it into that dictionary of data frames. Again, it doesn't have to be from our devices, as I showed in the other example. Here you could put in that pd.read_csv function to read in some other data. And now I have this dictionary of data frames, and I can use that dashboard again to show how this data in the time domain changed over time. And this is a nice view. There's 9 channels of data. This is a nice way to cleanly present it. I did update the x-axis here so they all match. So if I zoom in over here, it should zoom in on these other sub-channels so I can start to kind of correlate things. But I may want to focus on just the z-axis data. So again, I can use that function to pull all the data into one data frame and plot that in one plot here. And you see here now the time domain data from these 3 devices. You can see that long beam has a lot more acceleration, which makes sense. The shaker has less. The one on the short beam has a bit more acceleration because there's other frequency components there that are amplifying the vibration levels. So let's look at this now in the frequency domain. Here, I'm going to use our enDAQ.calc.psd to calculate a bunch of PSDs. So I'm looping through for every file. I want to get the z-axis data. I want to apply a high-pass filter at 2 hertz. Then I want to calculate a PSD with a bin width of 0.5 hertz. Then I want to add it to my master data frame here, but I'm going to force my frequencies to be rounded to the nearest 0.5 hertz so that they all have matching frequencies. And then here I get this final PSD. The shaker one was sampling a little faster, so my PSD goes a little longer, but that's okay. Now I can plot that. And so you see these three PSDs from three different files. And you see here the low frequency, that one that's on the longer beam has a resonance at a lower frequency than the one on the shorter beam, which is kind of obvious. I'm going to come back to that in a second, though. The one that was on the shaker should be reproducing what I told the shaker to do. And so this is roughly the profile I input into the shaker. It's rough because I didn't do good math, and I put in breakpoints that weren't perfectly octave spaced. So this doesn't look exactly like I wanted to, but I wanted to call out that you can reduce that PSD to 4 breakpoints, whatever you need with the octave spaced 2-octave function in our enDAQ.calc library. All right. As I mentioned, we have the PSD all in a shared data frame, and I can now get a transfer function to see how the impact of my natural frequencies in those two length beams are relative to the input vibration. And what's nice is people look to do transfer functions oftentimes with perfectly synchronized data, but with random data, you can actually do it with a PSD, and it doesn't have to be perfectly synchronized at all, and you get a really accurate transfer function. So here I've just divided the PSD of the long beam by the PSD of the shaker, and then take the square root of that, and then I have a G per G transfer function. You see here that long beam has a resonance of 24 hertz, has a second mode that starts to develop at 220 hertz, and the short beam, stiffer, has a first resonance at 80 hertz, and away you go. So the other thing I think is really cool, though, is I can double integrate this acceleration data to displacement. So here I'm going to loop through again. I'm going to do an integration to velocity, and then I'm going to do an integration to displacement. I'm going to convert my displacement data into units of inches, and then I am going to, down here, resample the data. This was all sampled at 4,000 hertz. I want to look at displacement. It's dominated by lower frequency content anyways. So I'm going to resample with our function to have a sample rate of 200 hertz. Now I can plot that all on one plot, and they're all, and this is the displacement, double integrated displacement of the three files. What I want to call out is when you look at this initially, you're going to go, where the heck is my shaker line? And it's actually here. If I zoom in, it's, the short beam has a little bit more of it has some higher frequency content there. So it's not perfectly matching the shaker, but it's still high frequency enough that it matches it really, really well. And what I also want to call out is that this is remarkably synchronized. I didn't do any manipulation to the time data. I resampled it at a frequency, but I didn't shift the start times. So it's synchronized. And you see here the start times of these two recordings are off by about a second or two because I pressed the button on two of them like this, and then I only have two hands. So I pressed the third device a second later. But just from the UTC time in our device, saving the calendar time, you have remarkably well synchronized data to within about 3 milliseconds, which I think is pretty cool. Okay, 30 minutes in, flying through this. I know I'm going fast, but there's a lot to cover. So my third story is I have some shock data. And I covered this in my blog on the shock response spectrum. I love this data set. It's from a customer who put one of our devices on a motorcycle and actually had a crash. It drove into a car and then recorded that. So that's pretty cool. So once I've loaded in that data, I want to plot it in the time domain. There's a lot of data in that file. And again, I could plot the whole thing, but I know that I have just one event. So I'm just going to focus at the peak event. And so we have a function here in enDAQ.plots around peak that you give it in a data frame of data. It could be acceleration data. It could be any data. It will find the peak across all the columns, so the max value across all the columns, and it will put that in the center of the plot as a default. But oftentimes you do shock testing, you may care more about what happens after the peak event than before, or maybe sometimes you actually care what was leading into the event. So we have another parameter here, the leading ratio. So it defines where in this window the peak is. And then the num of 1500 says I want to plot 1500 points per column. And so I can do that. And now I see my shock event in the time domain. And I haven't manipulated this data in any way yet. But before I show an example, I've used the high pass filter many times to get rid of the DC bias and other things I don't care about. But now I'm going to do a low pass filter. So it's the same function, filters.Butterworth. We just pass in the high cutoff of a particular frequency. And we can also use this as a bandpass if we also pass in the parameter of a low pass or a low cutoff. But here I'm looping through and I have the unfiltered data. I'm going to filter at 1600 hertz or 1600 hertz. Did I say that right? 800 hertz, 400, down to 50 hertz. So now I have one data frame of this various filtered data, and I'm going to plot that. So here's the unfiltered. Now when I filter it at 1600 hertz, you see it tracks it pretty well, but obviously it's getting rid of some frequency content above 1600 hertz. Now I go to 800, and you go to 400. And you see here it's still tracking overall the overall energy of the event, and we'll see that as I get into the integration for velocity. But I thought this is a nice, fun plot, and it's interactive again, so you can kind of play around and see. This is the filter data, 50 hertz, which is a pretty aggressive filter versus the unfiltered data. And one thing I do want to call out, and I always cringe, is when I see people with acceleration data and they look at the peak acceleration value, which is borderline useless and misleading. I really don't want people to look at peak acceleration. But if you filter it and then look at the peak acceleration, there starts to become a bit more meaning to that. And I'm going to show kind of why that matters in a second. All right, so I have this filtered data, unfiltered data, and various different filter frequencies. Now I want to do a shock response spectrum on that. So shock response spectrums calculate how a system responds given a range of natural frequencies. So you can define which frequencies you want to calculate this for. So we have a function to say, all right, here's my acceleration data. Build for me some frequencies that would be good to calculate on. So you can pass in your initial frequency, how many bins per octave, things like that, max frequency, I think. And now you can, once you have that, the frequency, the acceleration data, you have a function to calculate the shock response spectrum. The other parameter here is the damping ratio to use, and whether we want to do a shock response or shock pseudovelocity. So here's now the shock response spectrum of the various levels of filtering. And here is the pseudovelocity. It's the same function. We're just passing in mode equals PVSS. And this is a nice way to look at how the impact of filtering. Obviously, it only changes the response spectrum at frequencies above that. But one thing to notice is that the peak pseudovelocity of all these different filters, and again, I had a pretty aggressive 50 hertz filter in there, still has roughly the same peak pseudovelocity. Another function we have is a way to calculate an enveloping half sine pulse. So why that's helpful is, let's say you got, you have the shock response spectrum, you don't necessarily have access to a lab or a proper shock and vibe lab, but you do have the ability to drop something. So you can try to get a half sine pulse that roughly matches your raw data. And then once you have a good half sine pulse, you can figure out how to have a good drop stand to match that half sine. And so this function that Becker did, we wrote a paper on it, Becker did, and we presented it at the Shock and Vibe Symposium. It finds one half sine pulse that envelops that raw data. And here I went through and I did it on just two of the data, because there have been too many lines here if I put everything. You see here is this is the unfiltered data, and now here's the enveloped half sine. You see how it matches that peak pseudovelocity, and then it comes and it picks the highest acceleration if we're looking up here in this view in the SRS. And then if I can do that on the filtered data, and you see again it does the same thing. Oh, 200 hertz. So why I want to call this out though is, if you're trying to get this one with the unfiltered data, this might be 400G event with the 7 millisecond pulse width, might be hard to reproduce repeatedly, but you could, play with the filters you do and then the half sine that envelops that. And again, it'll still have the right maximum pseudovelocity. You just may have some higher frequency content that you're not able to excite as well. Okay, now because I have this data loaded, I can show the impact of damping. When you're calculating a shock response spectrum, one of your parameters is your damping ratio. And we always typically use damping ratio of 5%, which is Q equals a Q of 10, which is kind of industry standard, but I just want to call out that does matter. That does impact your pseudovelocity. Specifically, I want to show the peak pseudovelocity. So the peak pseudovelocity with a damping of 0 would be 650 inches per second. Okay, 650, remember that. All right. Now I'm going to take my data, again, just integrate in the time domain. So I'm just doing one integration to get velocity. And you see here, this is the velocity from that event. And if I look at the unfiltered data and I find my final velocity from the event, so this is the final change in velocity during my shock event, it's 653 inches per second. Whereas my peak pseudovelocity was 650 inches per second. It's one of the many reasons why pseudovelocity is a really, really nice way to characterize shock events. But that also shows an example of doing integrations for velocity. Okay, story 4 of 5. I'm almost done. This is another data set with some moving frequency content. It's now, I'm loading in a CSV file. It was data recorded by our device, but I just want to, again, use another example of CSV data. So it's on a motorcycle. And again, there's, how many data? There's about 4 million points here. I could plot this whole thing with that function or enDAQ.plots. Now I add in that opacity of 1. This view, again, would look identical to if I loaded everything and plotted everything. Yet this renders in seconds, and you still have the interactivity. Now, when you zoom in, it's pixelated, but you're able to figure out areas of interest. And when you're zoomed out, again, this image would be identical to an image if you loaded and plotted everything, which I think is nice. Okay, we're going to use our spectrogram function to show that frequency content change over time. It's on a motorcycle, the guy's revving the engine. This function returns the figure, which I'm displaying, but also returns my bins. And so I can use that here to pull out the peak frequency over time, which may be something you want to do. And you could start correlating peak frequency to other vibration metrics, but it's pretty easy to do once you have the output of that function. All right, my last story is our newer devices have a microphone. So I have the microphone on, and I went into our lab and I recorded a song from my phone of that song, that Gangnam Style song, and then I turned off my phone, and then I turned on our shaker system, which has a large, a loud blower. And in our lab, we have all these decibel meters because we're concerned about safety first, Hutchinson plants. I knew that the ambient noise level was in the 50 decibel range. And then when I turned on the shaker blower, we got into the 70s, okay? But here's the data recorded by the microphone. I did convert this to Pascals. I just want to call that out for people that have RW devices. You'll need to do this conversion, but in the coming month or two, we'll start doing this natively, so you get Pascal data from the start. Once you have Pascal data of a microphone, you can do a few things. One is you can save a WAV file, which I did here, and then you can play that. I'm not going to play this whole thing, but you can. I don't know if you can hear that. That's the good old Gangnam Style coming. So now I can convert this to decibels, though. So I do want to call that out. That is pretty helpful. I know Pete, our director of electrical and software engineering, thinks that's a nice feature for people to kind of take notes about the testing they're doing. Maybe record, hey, I put my device here. I'm going to do this test, and then do the test. And that sound data is preserved, and you can play it back. But we have a function in enDAQ.calc to convert Pascal microphone data into decibels. And that's what we're doing here. So when I had my phone directly over the microphone, so that was a pretty loud decibel there, but the ambient levels were in the 50s. And then once we turned on the blower, it came into the 70s, which is spot on. Really excited with that. We can also look at the frequency content of the microphone data with our 2-octave PSD. And then here I'm doing a spectrogram of that. And you see there's some interesting frequency content of the Gangnam Style song, and it kind of comes up, which is interesting as it hits, and then when I turn the fan on. Okay, questions, almost ready for questions. Last thing I want to call out though is one of the motivations for making this open library is we want to use that in the enDAQ cloud. And we want to allow, we have a free tier in the cloud that can generate these reports that it's similar, PSD shock response spectrums, pulling up the peak time history, doing these many, these sub channels on the bottom to see how things change over your recording. And this is nice and free, quick way to summarize a file in the cloud. But one of the big benefits too, though, is our cloud allows you the ability to customize the reports with your own Python code. And so that's the next step for us, is to take our open source library that's available in PyPI and bring that into our cloud, so you can start using these functions to customize reports with just a few lines of code, build a really custom report, pretty quickly, easy to read. So I'm excited about that. There's a lot of information about the cloud, and in the future webinars, we'll go into more about that. Now, before I open up for questions, I do want to call out that our next webinar is going to be us going through some user requested examples. So we have a form that I encourage you to fill out if you're interested in this, where you send us your data and how you'd like us to analyze it. And we'll go through and I'll generate a report for you using our open source Python code. I'll share that with you and I can walk through it one-on-one. And then we'll have another webinar to go through these examples in a month or so. We'll also be adding another function, another method or a module to our open library called enDAQ.batch to do a bunch of, if you have a lot of files, to batch process them. And then last is, as I mentioned, I want to show how to customize reports in the cloud, and we'll do that in early 2022. With that, Tina, I think I did pretty well. 42 minutes, we can open up for some questions.
Great. Okay, so we've gotten a lot of questions and a lot of interaction in the Q&A that the software team has answered, but we'll go over a couple of the outstanding ones and repeat a few of them as well. One of the questions that came in was about for shock testing. Why is using peak-to-peak signal, the no low-pass filter, why does that make no sense? How does the SRS change when using a low-pass filter?
Yeah, so that's a good question. Well, if we look at this, again, energy is related to velocity. And as you saw here, when I'm integrating the data to velocity, where did that go? There's almost no, or there's, maybe 10% difference between the final velocity of the unfiltered data versus the 50 Hertz filtered data. And when you look at it in the shock response spectrum or the pseudo velocity, you can very clearly see the impact of filtering. There you go. And they match up pretty nicely. Why you don't want to look at the peak acceleration in the time domain is I guess I don't know how else to describe how meaningless it is. I'm gonna have to write a blog to demonstrate how meaningless it is by going through a few other data sets. You can kind of look at it in my blog on the shock response spectrum. I compare acceleration data from a what's it called, an earthquake to a gunshot. And the earthquake has really low amplitude data, but that's a lot of energy that can really break buildings and tear apart various systems. But if you only looked at that time domain data, yeah, there's no damage potential in this data set. But that's just not true. And you need to take into account the frequency content too. Ideally, typically you're doing shock testing because you want to inform some design decisions. So you'll want to know, okay, I have the shock event. It's really being amplified if I had a natural frequency in my system at 50 Hertz. So I got to avoid that, or I have to add in an isolator. You can't get any of that insight by just looking at peak-to-peak acceleration in the time domain. That's impacted by sampling rate. It's impacted by just where you get the event. You could have the same sample rate, the same event, and get two completely different peak acceleration levels just based upon how the samples lined up with the actual shock. It's going to lead to more confusion and conclusions that may be misleading. I really strongly encourage people not to do that.
Another question that we got was, can we use the enDAQ Python libraries for just any vibration sensor systems as opposed to just ours?
Yeah, the only modules that won't be of use to you would be enDAQ.IDE, which is pulling out data from data sets recorded by our device. But once it pulls it out, it pulls it into a pandas data frame, which is the inputs for enDAQ.calc and enDAQ.plot. So you can get data in a structured data frame from CSV files, from MATLAB files, from any data set. So yes, enDAQ.calc and enDAQ.plot do not need to be, you get the benefits of that functionality without data, not having to use data from our devices.
There have been a couple of questions about if we're using a standard algorithm for calculating PVSS, such as an ISO 18431 or similar. I don't know if you can speak to that.
One of the benefits of open source is you can see. So you can go to the GitHub page and you can look at the source code. Becker, I don't know if you want to jump in and provide any more insight. I don't know exactly how Becker calculated it, but you can see in the source code how that was done. Anything to add there, Becker?
To be honest, not really. I'm not familiar with that standard. I can definitely say that we implement a particular transfer function with a biquad filter, and we do some zero padding on the end to get the full range of data for especially the lower frequencies. But aside from that, I don't think I have much meaningful information. Yeah, I would encourage people to look at the references that we have in the docs for shock, because those are the documents on which we base that calculation. Steve just highlighted the transfer function that we're trying to model for our SRS, and there's also a separate one for PVSS, which is lower in the relative displacement function. Yeah, unfortunately, I have to leave this as an exercise for the reader. Yeah. Sorry, guys.
Nope, that's good. And as Becker said, he referenced the paper by Howard Gaberson. I'm a big lover of the enDAQ, or the vibration data toolbox. It was developed by Tom Irvine. Becker and the other software guys can attest to the fact that every time they gave me a calc function, I would go try to reproduce it in the toolbox. We've done a lot of that testing. We've actually found some, maybe some things in the toolbox that weren't always correct, but we know that we're pretty proud of the shock response spectrum. I encourage people to check out the source code, try some tests, do some comparisons, and then let us know, ask us to explain why things maybe look a little different if they do.
Another question that we've gotten is it possible to process a bunch of files at the same time?
Yes, that's a good question. That's what Becker and our team are working on for enDAQ.batch. So that's going to be batch processing a bunch of files. You could kind of write that code a little bit yourself, which I did in a couple examples, whereas that, I loaded a few different files at once into one dictionary. I did that here. I did that this example. Where did that go? I don't know where it went. Here. No, I don't know. There's too much in this plot. Oh, here it is. So yes, more is coming on that. It's a good question. There it is.
Another question that we've gotten is, do you have constructed probability for the vibration data?
Constructive probability?
Constructed probability.
I don't know. We don't, because I don't know exactly what that question means, but yeah, certainly reach out and we can show how to do that. I don't know if it's a histogram, what it is, but I don't know.
All right, and is there ability to detect the output signal from the transfer function?
Becker, do you want to jump in there? I'm not sure I follow that question either.
I'm so sorry. I was reading. Question.
So the question is there ability to detect the output signal from the transfer function?
To detect the output signal. I'm not sure what's meant by that exactly.
I don't know. I don't know if they're referencing the example I went through where I calculate a transfer function with a few power spectral densities. But yeah, I mean, the raw data is there, so you see the response, but exactly.
Yeah. Yeah, definitely let us know if you're asking about like a Bodie plot or something, because that we haven't written a function for that, but that's on our radar.
Yeah,
for sure.
for the filters. Yeah.
Yep.
Another question we've gotten says, I don't understand the need to resample the data to a lower frequency for integrating to velocity and displacement. Can you explain the reasoning for that?
Oh, I didn't do that. In this example, I integrated to displacement without resampling. So here is just the raw data resampled. You still has the 40,000 data points to it. I could plot the whole thing. I just resampled for two reasons. One, I wanted to show that we have the function to resample. And two, once I've resampled it at a lower rate, I can just plot all the data and I don't have to worry about rendering speed and things like that. And it's displacement data. So it's really useless to kind of plot that sampled at 4,000 hertz. It's just, there's just going to be like no meaningful displacement at that higher frequency. But I didn't have to, and I didn't resample before I integrated. I resampled before I plotted.
Another question is there a way to walk through on our site about how a novice Python user can input their enDAQ data and get out a PVSS?
Yes, that might be a blog. I mean, I can walk through super quick right now. Is I have a data file. I know the channel, so I get acceleration equals the document and two pandas of channel 8, which is my analog accelerometer data. So I have acceleration. That's the first thing, 2 lines of code, you have acceleration. Now, if you skip down to here, I have the acceleration data. I want to calculate the frequencies to calculate my shock response spectrum. So we have a function to do that to log space the frequencies here based upon sampling rate and the length of the data set. So I have freaks. So those are the two parameters I have now, the acceleration data that I loaded with the 2 lines of code, the frequency bins I want to calculate the shock response spectrum at, and then I calculate my SRS with this function, with this line of code. So that'll be 4 lines, and then I plot it.
All right, and the last question that we have is, are there any examples included in the library, or would it be best to look at the collabs to kind of follow along with?
That's a really good question. For now, it's the collab, but we have been kind of racing against the clock to kind of get this out. We'll be adding more and more to the documentation for sure. We'll add more examples. As I mentioned too, our next webinar is going to be going through more examples. So if you guys have specific examples you want us to cover, please send us that request and the data, and we will go through and show those examples. We may actually add some functionality to the library too as we go to satisfy the needs of those requests. But yeah, and we'll also be looking to add better and better documentation to show examples. But for now, it's basically this collab and the documentation. But more is coming, especially the next webinar.
All right, and that kind of concludes our question and answer session.
Great. Well, thank you, everyone. I'll give it back to Tina again. More is coming in terms of documentation, functionality, you name it. So this is really just a start, but we're still excited to be here. And please don't hesitate to reach out with questions. We're really motivated to help people get started using this tool we've developed. Tina, take it away.
All right. So thank you everybody for attending today and for all your great questions and interacting with us so much in the Q&A and in the chat. It's great to see what you have to say. So We hope you found this webinar very helpful and informative, and that you're ready to start using the enDAQ Python library to simplify your shock and vibration analysis. If you have any other questions or think of something later, don't hesitate to contact us. We'll send out an email in the next few days with a recording of this webinar and links to some helpful resources. Just a reminder that this webinar is part of our Python for Mechanical Engineers series. Our next webinar on custom analysis of your real shock and vibration data with Python in the enDAQ library will be on December 2nd at 12 p.m. Eastern Time. If you're interested in submitting your data files for a live analysis, you can head to our submission form on our website. We've posted the link in the chat, and we'll also include it in our follow-up email. Once you submit your files and a brief description of your data and what report you'd like to generate, Steve will reach out to set up a meeting to establish the best way to customize your analysis. And just to reiterate what Steve said earlier, this data will be analyzed live in our next webinar, so make sure you feel comfortable sharing your data and that you have the permission to do so. Finally, once we close the webinar, a feedback survey will launch. Like I said earlier, we'd love to have your feedback on this webinar so we can improve our content and ensure we're providing relevant resources that can help you with your analysis. Again, from all of us at enDAQ, thank you so much for joining us today. We really appreciate your time. Take care. Bye.
Thank you, everyone. Talk soon.